Hello everyone. Today we're going to talk about a really important concept in calculus, and it's continuity. So to illustrate this point, we're going to take a look at two different bridges. Okay, looking at these two different bridges, you can see that the one on the left, a car would be able to travel from one end to the other without a problem. It is a continuous drive. And so this graph is continuous, therefore shows continuity. Obviously, the one on the right, as a car is driving, it is not, in fact, going to be able to get to one end to the other because it is discontinuous. And this is a pretty clear, I think, picture of what the idea of continuity is. Synonymous with discontinuous, we can say it shows discontinuity. And the idea is for a graph, the way I always explain a continuous graph is that if I can put my pencil on the far left-hand side of the graph, and if I can keep my pencil tip as I'm graphing from left to right and never have to pick it up, then I know it's continuous. Kind of just like these pictures of these bridges right here. Okay, so it's really important that we understand there are three main rules for us to not have a continuous graph. The first one is that we cannot have a hole in our graph. Okay, so there may not be a hole. And of course we know a hole looks something like this in the graph. Okay, the second rule is that there can be no breakpoints. Sometimes I call those also jumps. And that's when you have a graph where it's coming from one side and then it picks up. Okay, a lot of our piecewise functions look like this. Okay, that point right there, that x value, is considered a break point where it breaks and it jumps from one to the next. Okay, and the third one is we cannot have any specifically vertical asymptotes. And that's very important that we understand that it's the vertical asymptote that we can't have. So, these are ones where we might have something that looks like that. Okay, it is the vertical asymptotes that we need to stay away from. Okay, looking at the graph here, they're asking us to state the intervals over which the function is continuous. So take a minute, get that graph copied down in your notebook as best as you can. And then we're going to go ahead and get started on naming all of the x intervals over which this function is continuous. So I want to start over to the left-hand side of the graph, and it looks like it starts there with an endpoint at -12. And so we have a bracket, -12. And you can see that it travels along until there is a break. There's a hole at -8. And because that's an open circle, we're going to go ahead and use a parenthesis. Okay, then it picks up again at -8 and continues on until -2 with a bracket because it's a closed circle. You can see that I'm not exactly sure then what's happening after that -2. You can tell it's a jump. And so we're going to go ahead and use a open parenthesis, -2, because we know it was closed at the point -2, 3. So it must be open wherever that's coming from on the right-hand side there. So we're going to go open -2, and then it travels all the way over here till 6, and again with an open circle, and then it jumps. And so we have a closed circle at 6. So we're going to go ahead and put a bracket. And then you can see that that travels along for infinity and even has an arrow at the end, so we end up with this. So over those intervals, the function is continuous. It is at our holes, our jumps, and even what kind of looks like here a vertical asymptote, although it must not be because -2, 3 is a point. But for those values is when we would say that the function is not continuous or shows discontinuity. Okay, this next question is a huge concept, and I really want to make sure you get this down in your notes and you star it and you have to memorize it. How to determine if a function is continuous? Well, we're going to use the definition of continuity in order to answer that question. Okay, so if a function is continuous, well then this is the criteria that has to be met. The limit as x approaches a from the left of that function must equal the limit as x approaches a from the right for that function. Okay, so if you just stop there and think for a second, what does that mean? Well, if the limit as x approaches a from the left is the same as the limit as x approaches a from the right, it means the limit exists. Okay, and then if we take that one step further, those limits have to be equal to f of a, so the function at that x value a. Okay, so like I said, this is a huge concept in our course. So we definitely want to make sure that we have that memorized and that we're able to recite it back. All right, now let's just kind of break it down and make sure that we understand graphically what this is all about. So, and if we have a graph and we're talking about an x value of a, okay, the first two concepts here are saying that if the limit as x approaches a from the left and the limit as x approaches a from the right are equal, well, what that's looking like is if I have a graph coming in from the left and coming in from the right, that from both sides I'm going to end up at the same height. Okay, so that's what that's saying, that limit exists. But the next part of it here, because of course right now the way I have it graphed, it's a discontinuous function. It's a hole in our graph or in our bridge. It's not connecting from one side to the other. So in order to make it continuous, this next part is very important. It's saying that the height at A has to be that same height as the limit. It's saying that these values have to be all three the same. So there cannot be an open hole in our graph that closes it off and makes it a continuous function. Okay, there are some people who like to look at this, and especially this left-hand side, and they just kind of condense it a little bit, and I just wanted to bring that up. It's okay that they do that. They say just that the limit as x approaches a of the function is equal to f of a. And of course, we learned a couple classes ago that if our limit as x approaches a from the left is equal to the limit as x approaches a from the right, that is in fact the limit as x approaches a in general. And so it is, like I said, condensed in the condensed form. This is also true, but the way that I would really like you to memorize it and the way we're going to practice it over and over again is following the initial way that I said it. If the left is equal to the right is equal to f of that same x value, then we in fact have a continuous function. Alrighty, so we are going to look at several examples, and a lot of these are very similar to problems that are actually on your AP, and we're going to be studying these and practicing these all year long. So let's get this first one down. And it's asking us to determine if the function is continuous at two different values, x equals -1 and x equals 6. So if we take a look at this, you can see that -1 and 6 come up here at what we would call our breakpoints. So as we determine if in fact the function is continuous at those values, we are going to use that definition that we wrote out last time for each of those x values. So we're going to start with the limit as x approaches -1 from the left of f of x. And we're going to see if that's equal to the limit as x approaches -1 from the right of f of x. And if that is equal to f of -1. Okay, so we're going to do this one at a time and take a look at it. So if I'm asking to evaluate the limit as x approaches -1 from the left. Well, from the left is asking for numbers that are to the left of -1. So numbers to the left of -1 would mean x would be smaller than -1. And so we would want to use this first piece of the graph, okay? And so of the function. So if we're using this one right here, okay, we're going to go ahead and use that, but we're going to plug in -1. And I just kind of do a real quick check in my head to make sure that as I substitute in the -1, that it's not going to give me back one of those 0 over 0. So if I put that -1 in, okay, I get 2 times -1 plus 6 all over -1 squared minus 9. And so looking at that, that's -2 plus 6 is 4 over 1 minus 9 is -8. Okay, so -4/8. And we're saying, is that equal to the limit as x approaches -1 from the right? All right, so again, now from the right, we're now looking at when x is greater than -1. So we're looking at this next function that's listed. Okay, so using this one now, again, if I just kind of in my head think about plugging -1 in here, I can tell that it's going to be fine, that I can plug it in. I'm not going to have to do any factoring. So 2 times -1 minus 6 over -1 minus 4. And so 2 times -1, -2 minus 6 is -8 over -5. And so -8 over -5, clearly 8/5 is not the same as -4/8. So I can actually stop right there, because what that determines is, excuse me, is that the limit as x approaches -1 is not the same from the left and the right. Therefore, the limit does not exist. Okay, so this limit does not exist. And so therefore, it can't be continuous. In order for a function to be continuous, the limit must exist at that x value. And what does that mean for the limit to exist? It means the limit from the left and from the right are the same value. And you can see, though, if we wanted to finish it out and look at f of -1, just a little bit of review here. If I want to evaluate f of -1, I would be looking for when x was equal to -1, which I've already evaluated over here, so I can already just kind of plug that in and say that I know that it's 8/5. But even though these are equal, the second and the third condition, it doesn't mean that it is continuous. All three conditions must be equal in order for the limit, in order for the function to be continuous. Okay, as far as the directions up here, justify your answer. This work right here, that's your justification. Okay, you showing that the limit from the left does not equal the limit from the right is your justification that in fact it is discontinuous at x equals -1. Okay, so we're going to go on to the next one, the second half of this question. Okay, so looking at the second part of this question, it's asking us to determine if f is continuous at x equals 6. So same thing. I'm going to set up is limit from x approaches 6 from the left of f of x. Is that the same as limit as x approaches 6 from the right of f of x? Which is that the same as f of 6? Okay, so same thing. I'm looking at as x approaches 6 from the left. That would be when x is less than 6. And so I'm using this second rule right there. And I'm plugging that in. Mentally, I can see that as I chug in the 6, it's not going to make zeros in the top or the bottom. So I can kind of figure that out. So 2 times 6 is 12. Minus 6 is going to be 6 over 6 minus 4 is going to be 2. So that's going to give me a limit of 3. Okay, is that the same as the limit as x approaches 6 from the right? So from the right, we're coming from the right-hand side of the graph, so numbers bigger than 6. So we're looking at x when x is greater than 6. So we're looking at the second rule, the square root of x plus 3, which is the square root of 6 plus 3, square root of 9, which of course is 3. Okay, so far so good. We have a limit that exists. But in order for that limit to exist and be continuous at 6, we need to evaluate f of 6 and make sure it also is 3. So f of 6, okay, is asking when is x equal to 6. So you can see that x is equal to 6 here. And so therefore we're taking that first rule that we were working with over on the left-hand side here. And so we can tell that f of 6 is in fact 3. And so all three conditions are met. And so we can say yes, continuous at x equals 6. All right, good job. Alrighty then, let's get this next one down and we're going to determine if g is continuous or not at x equals 1. All right, so right away, as soon as we hear that question, we know we're going to go ahead and write down this condition, the limit as x approaches 1 from the left of g of x, make sure you're using g of x this time, is equal to the limit as x approaches 1 from the right of g of x, which will have to be equal to g of 1. Okay, so we're going to evaluate each of these pieces, and we're not going to be freaked out by the fact that we have some natural logs and some trig functions and some exponential e-based functions, okay? So we're going to go ahead and first of all do x from the left, which of course means that x is less than 1. Okay, so we're going to go ahead and plug in 1 into this first top expression equation. So natural log, of 1 plus cosine of 1 minus 1, so cosine of 0. Okay, so if we think about our natural log graph, all right, we know our natural log graph looks like this. And what is that point right here? We should know it as 1, 0. So, in fact, natural log of 1 is 0. The other way to think about that is, remember, natural logs are a type of log, okay? And so you're saying what base, what power do I have to put on a base, in this case a base of e, to give me back a 1? Well, we know that anything raised to the 0 power is 1, and so that is where that answer comes from. Okay, plus cosine of 0. So again, let's just take a quick second to think about our cosine graph. We know it looks like, well, not exactly like that, but we get the idea. And we know that at 0, the height of cosine is in fact 1. And so we're going to get 1 for that limit as x approaches 1 from the left. Okay, now let's look at it, the limit as x approaches 1 from the right. I know it's hard to read here. That's e to the 1 minus x plus 2 sine pi x. Okay, so we're going to go ahead and evaluate that. And again, like I said, we're going to now use the second thing because we're looking for x is greater than 1. So that would be e to the 1 minus 1 would be e to the 0 plus 2 sine pi x would be pi times 1, so 2 sine pi. Okay, and we're going to see if these are the same. So e to the 0, anything to the 0, we just talked about, anything to the 0 is in fact 1, plus, okay, looking at our sine graph for a second here. Our sine graph looks like this, and here, right here is pi. So sine of pi is in fact 0. 2 times 0 would be 0. So we do get 1 back. So that confirms that the limit as x approaches 1 does exist. The limit exists at 1. And because one of our two values up here was equal to 1, in fact, the very first one, we can tell that g of 1 is also equal to 1. So we would say, yes, this is continuous at 1. Okay, good job. All right, moving on to the next one. Okay, ladies and gentlemen, looking at this next one, determine if h is continuous at x equals 2. Okay, looking at our conditions on the right-hand side, we'll notice that it's a little different than the last ones we've been looking at. Instead of having inequalities, we have a piecewise function for two general conditions, x not equal to 2 and x equal to 2. It doesn't change the approach or the way we go about this. We're still going to look at the limit as x approaches 2 from the left for h of x. And we're going to see if that's equal to the limit as x approaches 2 from the right of h of x. And if that's equal, in fact, to h of 2. Okay, so as far as the left and from the right, when you don't have inequalities, well, basically, when x is approaching 2 from the left, that would be coming at numbers smaller than 2. Namely, smaller than 2, not equal to 2. And so, as x is approaching 2 from the left or from the right, we're looking at this top condition not equaling 2. The only time we're going to be looking at equaling 2 is for this last, our third thing that we have to evaluate, h at 2. And that one we can do right away. H of 2, we can see here that when x is 2, the output is in fact 3. And so that one we know right away. Now, the limit as x approaches 2 from the left and the right, those are values that are not 2, they are approaching 2. So that's why we're going to use this top problem, which of course so I'm going to erase that so you can see. All right, so we're going to go ahead and plug into that top rule. And as I look here, I can tell that if I plug 2 in to evaluate the limit as x approaches 2 from the left, when I plug that 2 in, I can tell I'm going to get a 0 in the denominator, 4 minus 4, and I'm also going to get a 0 in the numerator, 4 minus 16, negative 12, plus 12 is 0. So I'm going to go ahead and factor that as I take a look at this. So that's going to be x minus 6, x minus 2, and the bottom 4 minus x squared would be 2 plus x, 2 minus x. And so in fact we can see the whole there that we're going to be able to cross out and leave a negative 1 behind. And so now when I go ahead and put that 2 in, I won't get that 0 over 0. So 2 minus 6 is negative 4 times that negative 1 over there is going to be a positive 4 in the numerator. And then 2 plus 2 is going to give me a 4 on the bottom, which is obviously 1. Okay, the limit as x approaches 2 from the right. Well, as I just said, we're going to use the exact same function because 2 from the right is again when it is not 2, it's approaching 2. And so my only choices are not 2 or 2. And so we're going to definitely go ahead and use that top one again, which again will be 4 over 4, so 1. So we can see here that the limit from the left is equal to the limit from the right, but in fact that does not equal h at 2. And so this is a unique situation where we have here a graph where the limit exists, but it is not continuous. Okay, so the limit exists, but it is not continuous. So just kind of taking a look at what would that mean graphically, how would that picture play out? Okay, so what we'd be looking at is a graph. Okay, and we can see here that the limit as x approaches 2 from the left, okay, is going to reach a height of 1. So the graph might come over like this, and it reaches a height of 1. And the limit as x approaches 2 from the right is also going to come and reach a height of 1. But this part of the last part there, that the h of 2 is in fact 3. So the picture I drew right now shows that the limit does exist. As I approach from the left and from the right, I am reaching the exact same height. But this last part, that h of 2 is equal to 3, that throws the wrench into our graph being continuous, because now it's telling us that when x is 2, the height is actually 3. So we have this closed circle up here. And so that confirms the fact that we have a hole in our graph, therefore it's not continuous. Okay, so we're looking at 2 more examples with these notes and then we're done. Okay, so and both of these are pretty common questions on the AP, so let's make sure that you get it down and that you have a just a firm grasp of what's going on. All right, so this is asking us to find the value of a so that the function is continuous. So here's that idea of continuous function again. Okay, so again to review, in order for the function to be continuous, the limit from the left would have to equal the limit from the right. In other words, the limit needs to exist, and that point needs to also exist. Okay, so we're going to start by just looking at the first part of that definition. Okay, the first part of that condition, that the limit as x approaches -2 from the left of h of x is going to have to equal the limit as x approaches -2 from the right of h of x. All right, so if you look here, we have multiple variables in our problem, okay? That's all right. That's what we're going to work through. So we're going to get down what we know must happen in order for this limit to exist, in order for the limit from the left to equal the limit from the right. Well, going from the left-hand side, okay, that would be this one right here, because numbers to the left of negative 2 are smaller than negative 2. So we're looking at 2x squared minus a from the left-hand side. Okay, and on the right-hand side, the limit as x approaches negative 2 from the right, well, that's looking at the second rule, when x is bigger than negative 2. So we're looking at ax to the third plus 3x. All right, now I do not know what a is. That's what I'm looking for. But in fact, I do know what x is, okay? I am looking for when x is approaching negative 2. So I know that that's what I would directly substitute in for x would be negative 2. So I'm going to go ahead and evaluate this and plug in negative 2 for x. So 2 times negative 2 squared minus a is equal to a times negative 2 cubed plus 3 times negative 2. All right, so this is going to give us 2 times 4, so 8 minus a is equal to a times negative 2 cubed, so that would be negative 8a, and then minus 6. Okay, so now what I'm left with is a very simple equation that I should be able to solve without a problem, and that's going to help me finalize and find my answer. So if I add 8a over here, I'd get 7a, and if I subtract 8 from both sides, I'd have negative 14, and so a here is in fact negative 2. And so I've found the value of a that makes the limit exist. Okay, ladies and gentlemen, this last problem that we're faced with is quite the big one. It definitely is a higher level of difficulty, so make sure you stick with me and get it all copied down. Okay, so this time we're finding the values of b and c, so we're finding two different variables so that the function is continuous. All right, generally when you have to find the values of two different variables, they're going to give you two different breakpoints. And if we look here at our conditions, in fact, we do have two different breakpoints. We have one at negative 2 and one at 3. And so when we have two different breakpoints, we're going to have two different rules, two different formulas that we have to, two different conditions that we have to satisfy. Okay, so we're going to go ahead and write those out. One for each breakpoint. So the limit as x approaches negative 2 from the left of f of x has to equal the limit as x approaches negative 2 from the right of f of x. Okay, so that's the first one. All right, and then we're also going to look at the limit as x approaches 3 from the left of f of x, and the limit as x approaches 3 from the right of f of x. Okay, so we're going to look at both of these one at a time, and then in the end we're going to end up kind of merging the two of them together. All right, so first let's look at the one on the negative 2 condition here. Okay, so as x approaches negative 2 from the left, so that would be when x is less than negative 2, we're looking at cx plus 3b, and that is going to be equal to negative 2 from the right, so that would be when x is greater than negative 2, so we have bx squared minus 4. Okay, moving over to the other problem, okay? Same idea. First one is x is approaching 3 from the left would be when x is less than 3. So bx squared minus 4. And then 3 from the right would be the cx cubed minus bx. Okay, so now for both of these, the same way that we did it last time, okay, we're going to go ahead and plug in our respective x's in for these problems, leaving b and c as b and c. So on the left-hand side here, we'd get negative 2c when I plug in negative 2 for x, plus 3b is equal to negative 2 squared is 4b minus 4. Okay, so the only thing that I can kind of clean up is I can move my 3b over here to the right-hand side. So I have negative 2c is equal to b minus 4. All right, so from this point forward, we're not really sure exactly what we're going to do any further with that, so we're just going to leave that for a second, and we're going to move on to the second formula that I have written here on the right-hand side. All right, so we're going to go with that one. Same thing. This time I'm going to put 3 in for x because now we're looking at the limit as x approaches 3. So we're looking at 3 squared, which is 9b b minus 4 is equal to 3 cubed, which is 27c minus 3b. Okay, and just like on the other side, I can kind of clean that up with one more step by adding the 3b over. So I'd end up with 12b minus 4 equals 27c. Okay, now I want to kind of take a step back and look at my two equations. And if I look at them, I can see that one of the equations, namely the one on the left, it's easier to kind of get to isolate one of the variables. So what we're doing here is we want to use the substitution method for solving systems of linear equations. We want to isolate one of the variables and then take that expression and plug it in for the other one. So this is something way back from freshman level. Or 8th grade level, and we're going to go ahead and apply that here. So if I look at my two linear equations, I can tell that the one on the left hand side here is much more manageable in order to isolate one of the variables. Okay, so we're going to do that by going ahead and adding the 4 over to both sides. So what we'll end up here with is b is equal to negative 2c plus 4. All right, so then what we're going to do is go ahead and take that expression for b and plug it in on the other equation. All right, so we're going to go ahead and do right now. So we're going to take and replace the b with that negative 2c plus 4. Okay. All right, so now we have an equation that relies on only one variable, so we should be able to solve for c. I'm going to start by cleaning this up. So negative 24c plus 48 minus 4 equals 27c. Okay, so negative 24c plus 44 equals 27c. All right, we want to join our c's to one side, so add the 24 c's over. And so we get 44 is equal to 27 plus 24 would be 51c. And so to isolate the c, we divide by 51, and we actually end up with this kind of ugly answer, 44 over 51 for our c. And that's okay. That shouldn't freak us out. Okay, so that next step then is to take that 44 over 51 and plug it back in over here for c to solve for b. Okay, so we're going to go ahead and do that. B is equal to negative 2 times 44 over 51 plus 4. All right, so this would be on the non-calculator part of the exam. And you can see these are pretty ugly fractions, and that's okay. That's something that you have to be comfortable with. And I've talked to some of you about getting better about adding and subtracting fractions in your head and even multiplying here. This negative 2 is like negative 2 over 1. So when you multiply times 44 over 51, that would be negative 88 over 51. And we're adding that to 4. Okay, so it looks like I need to get a common denominator here of 51. Okay, so clearly the left-hand side is fine, negative 88. And then if I multiply 4 times 51, it's actually just 204. And so now when I'm adding 204 and negative 88, I end up with 116 over 51. And so that is my b value. And over here I had my c value. So I end up with both answers for this very large mammoth problem. All right, so good job. Way to stick with me on that. In class, we will definitely be practicing these and all the other ones that we did. Make sure that you come to class knowing the definition of continuity. Make sure that you can recite that and that you have that prepared. Okay, thanks a lot. Good job.